Remember, y'all's AI thing is due then this week. Remember, it's just to motivate you all to engage with AI/LLM in a way that is actually learning with it, as opposed in a meaningful learning. There is learning done by just asking it a question and spitting out an answer, but it's fairly shallow. It's just like facts, information. But actually engaging with it in a conversation kind of way, it's something you're going to be doing. If I was a betting individual, I'd bet money on it's a skill you're going to need in the future. You can come back to me in 10 years and tell me whether or not I'm wrong or right. But yeah, there's just too much money going into it for it to not be a thing. All right, so anyhow, do that. Pretty straightforward. Just grade on whether you do it. My lecture class had some good questions. Like, does it have to be physics questions that you engage with it? No. It just needs to be something that requires critical thinking and that has some complexity to it. So if it's one of your engineering courses, if it's your computer science, I really don't care too much the context. What I do care is that it is something that has complexity and critical thinking. Whatever that might be. Heck, if you use it to fix an appliance in your home, I'd even count that. You're using it to learn. All right. But yeah, if it's super simple, you're not going to really need it. So that's why I want you to have something that has complexity, something you don't know how to do with multiple steps. So there's that. Otherwise, I uploaded the PowerPoints we're going to get through today. Finish up magnetic fields. This one we'll start Faraday's law. And then after that, so my hope is that today we're going to definitely finish this PowerPoint. We're going to start Faraday's law for sure. Thursday, we're going to hopefully either get close to finishing or finish Faraday's law. And then next week, we'll start talking about AC circuits, inductors and AC circuits, and we'll start to mention some of those things today. And that'll be it. That'll be what the test is on. AC circuits, the last thing we're covering is very formula stuff. So it's like very plug and chuggy kind of stuff, fairly straightforward, not much complexity to it. Faraday's law, the stuff that we're going to start talking about today, that is going to be as concept heavy as the stuff we've been talking about up to this point. But it's super, super important. I would argue, yeah, it's super important. I mean, it's going to explain how we make electricity. Like just from what we're going to cover in this 1 week of PowerPoints, you'll understand how 95% of all electricity is generated. So it's pretty impactful. All right.
Two windmills are standing in a wind farm. One asks, "What's your favorite kind of music?" The other one replies, "I guess I'm a big metal fan."
Because it's a windmill. It is a big metal fan. It's a fan made of metal. I don't know. I feel like I don't know this one. Okay, I don't know how that one landed. It's a great joke. It's even better when it's like, anywho, think about it. Go back and listen to the recording.
We should have done it like one, like we're with fans.
All right. So to summarize what we've been learning in this PowerPoint, because we've been working on it for the past week, we have found the magnetic field due to an arc of wire. There's the equation for it. Mu naught I theta over 4 pi r. We have then found the magnetic field due to a finite piece of wire. It's mu naught I over 4 pi r times cosine theta 1 minus cosine theta 2. We then figured out how to make this an infinite wire. That was the two clicker questions after this. We made theta 1, 0, theta 2, pi, and boom, we derived the equation for the infinite wire. Mu naught I over 2 pi r. So we have the equation for the magnetic field due to an arc. The equation for the magnetic field due to a wire. And then we basically said, what if you have multiple wires? Well, you just find the magnetic field due to each one. They're vectors. You combine them, doing vector math. So we practiced that a bunch. Did a couple problems on that. A lot of fun. Then we found that if you had two wires, one makes a field, the other experiences a field. So we kind of put everything together for the past 2 weeks. We found the force on a current-carrying wire due to another wire. And we solved the problem on that. 3 wires. Find the force in the middle one. And that's where we left things off. So basically the prevailing thing here is current-carrying wires make magnetic fields. And currently we've learned 2 different types of wires. Arc of wire and a straight wire. What we're going to finish up with is we're going to learn Ampere's law, which is going to let us find the magnetic field. What if you're inside a wire? We're going to find the magnetic field inside wires, or if you have a bunch of them, if only it was 0. It sadly isn't. And we're going to learn about a solenoid, which would be the last geometry. A solenoid is just an insulated slinky. So we'll see that when we see that. And that'll kind of finish up this one, and then we'll get into Faraday's law. So, Ampere's law. I'm just going to straight up just tell you the Ampere's law. I can't really derive. The derivation for this is a lot. But it's a law, so I can just tell you, I can hand wave it and say it's an observation of reality, because it kind of is. The observations that led to this, we're not going to spend the time on, because it's not a simple thing to explain. I looked into it, and I was like, this is too much, so I'm just going to say, hey, here it is. The integral of b dot dl equals mu naught I enclosed. Now, I hope when you look at this, that this looks kind of familiar. That you all have seen another equation that looks kind of familiar. Does anyone know what the other equation is that looks kind of like this, that has some closed path integral on the left and then has something enclosed on the right? It's like Gauss's law. And we're going to use it in the same way, but it's simpler. This one's going to be a little easier. So it's going to be a nice kind of review of Gauss's law in some ways. And it's going to be easier because instead of 3 dimensions, we're just going to work in 2 dimensions. You'll see what I mean as we solve things. And instead of having 3 different scenarios, Gauss's law was for a line of charge, a plane of charge, or a sphere of charge. We are only going to use Ampere's law for one scenario, which is a straight wire. We already solved a straight wire. We solved outside of a straight wire. We have not solved inside a straight wire. So this is going to let us do that, or if we have multiple wires. So yeah, it's going to be great. It's not going to be it's going to be pretty straightforward. And just to remind you all of Gauss's law, this is what Gauss's law looked like, just so we can compare the two. So Gauss's law was E instead of B. It was an area instead of a length. And it was Q enclosed instead of I enclosed. And it was over epsilon naught instead of times mu naught. But the process is going to be very similar. So this is going to be a really good review. And the problem we're going to work on is going to look like one you've already seen. With that used for Gauss's law. But we're going to do it with Ampere's law instead. Different purpose. But it's going to look real similar once we draw a picture. That's the hope at least. All right. So to do Ampere's law, we don't want to do an integral. Remember, Gauss's law, you never actually did an integral. In any Gauss law problem, you never integrated anything. The same is true of Ampere's law. That integral on the left, I don't actually want to do an integral. How do we avoid doing an integral? There's 2 ways we can avoid doing an integral. If b dot dl, so just a reminder to you all, a dot product is the same as multiplying the magnitudes times the angle between them. So I'm going to write this out just to prove a point. So we don't want to do an integral. So our choices are to make b a constant so that it comes out of the integral, and then we're just going to integrate dl, and that's just L, or to make the angle between b and dl 90 degrees so that the integral goes away. So either we want constants, or we want the angle between them to be 90 degrees. So that's going to segue us into this problem for you all that you can definitely solve. I have a straight wire. I want to choose a path around this wire such that everywhere on that path, the magnetic field is a constant. What path should I use? So just to show you what I mean, I'm going to kind of draw these paths. I'm going to draw each of them. So when I say circle, I mean we're going to draw. So our goal here is to find the magnetic field at some point P. To do so, we're going to draw our, not a Gaussian surface, we're going to draw an Amperian loop. We're going to draw a fake loop around it. What should the shape of that loop be? Should the loop be a dotted circle? So we always make them dotted. So that's a circle. Should it be a square? Should it be a triangle? And all of these are going to intersect that point. Or should it be a figure 8? It's going to be real fun to draw. Great. Which path that I just drew, which path has a magnetic field a constant everywhere on it? The value of B is constant everywhere on the dotted path. Circle, square, triangle, or figure 8. I believe in you. Yeah. It's a circle. Why? Because everywhere in that circle. Yeah. Okay, great. So that's the shape we're going to draw. All right.
I know.
Oh. All right, give you all about 15 more seconds. It's looking good. All right, in 5, 4, 3, 2, 1. All right. So hopefully I've said this enough time. What does a magnetic field look like around a wire? A circle. Why do we draw circles? Because the magnetic field is the same everywhere on that circle. Yay, the answer is circle. Now, not only is the magnetic field a constant everywhere in that circle, if we pick a piece of that circle, the magnetic field, I'm drawing the magnetic field lines. Remember, they make the circle. So at various points, they point tangent to the circle. Which way does DL point? DL is in the direction the circle's going. DL is in the same direction. Everywhere on the circle, DL is also tangent to the circle. Why does that matter? If DL, so if we look at this, B dot DL, remember, it's just going to be B times DL times cosine of theta. So B is a constant, so we can pull it out. If they're parallel to each other, if B and DL are parallel, what's the angle between them? You got this. If they're parallel, 0. B gets pulled out. DL stays in there. Cosine of theta is 1. Why? Because cosine of 0 is 1 because they line up. Yay, it's going to be B times L. Now, my question to you is, what is the length of a circle? 2 pi r. You did it. So this is how we're going to use Ampere's law. It's always going to be a dotted circle because we're only going to use it for a straight wire. There's only 2 scenarios we can use it for, a straight wire and a solenoid. And the solenoid, I'm going to use it to derive the expression. You won't actually have to do it yourself. So we're pretty much always going to do a straight wire. Draw a dotted circle. Solve for B dot DL. It always turns into B times 2 pi r because the length of a circle is 2 pi r. Now, the part that is usually actually more challenging for people is finding the current enclosed. You all found charge enclosed before. It's going to be the same technique. If you have all the current, then put that as your current enclosed. If you have none of the current, then put 0. If you have some of the current, you're going to find the current density. And you're going to then, so we're going to do, we'll do it when we do it. Just like you all found the charge density, and it was a ratio of the total charge over the total volume equal the enclosed charge over the closed. Instead of volume, it's going to be area. So I put that here multiplied by area enclosed. So just to show you all this, so say we had a big fat wire like this that has some current I, and I wanted to find the current enclosed. I want to find the magnetic field at some point here. Let's call this little r. Let's call this big thing capital R. How do I find the current enclosed? We use a 2D. So we're going to use sigma, that's 2D. And that's going to equal the total current divided by the total area. And that is going to equal the enclosed current over the enclosed area. We did a similar technique with charge. Here it's 2 dimension instead of 3 dimensions. And then you just solve for I enclosed. We're going to do that in the next problem. So I'm going to kind of leave it here for now, but the next problem we're going to practice this. If there's multiple wires enclosed, then you find the current enclosed for each of them and add them together there is a caveat to this. The direction of current matters. So we don't have like so in charge we had positive and negative charge. When it comes to current, we have positive and negative. How we define positive and negative? The direction. The direction of current is going to tell us whether it's positive or negative. And we're going to see an example of that later on. So I won't spend too much time on that right now. Okay, so let's do a really easy example here. And I'm actually going to change this example. I'm just going to derive it for y'all. Use Ampere's law to find the magnetic field r meters away. I'm just going to put a distance r away from a wire with a current equal to I. And we're just going to find the magnitude of it. So it doesn't specify which way this current's going. Let's just say it's out of the page for funsies. I'm going to help you all draw the, you know what, you all draw the picture. There's my current carrying wire. I'm a distance r away from it, so I'm outside the wire. Go ahead and try to do this. B.dl equals mu naught I enclosed. We are trying to find the magnetic field some distance r away. So try that process I just taught you all. You got this. You can do it. I believe in you. And you're solving for B. This should be able to be done in like 3 or 4 lines. It's a really short problem. If you're stumped, look at the previous PowerPoint and just go through the steps. What's I enclosed going to be in this problem? What's I enclosed going to be in this problem? Yeah, what's the direction? What is, so I enclosed right now is kind of, what is the current enclosed by your rule? How much current do I have?
How much?
Yeah. What's the variable that represents it? Just I. Just I. Yes. No, you don't want to, because I enclosed, you haven't actually found it yet. And this problem is I.
Okay.
If I had said it was 3i, then it'd be 3i. Yep. That's it. You derive the expression for the magnetic field in the infinite wire.
Yeah.
In 3 lines. Yeah. It's much easier than doing integration. So first step is you draw a dotted circle. So great, there's a dotted circle. Again, I'm just doing the steps that are listed. Then solve B.dl. It tells you what that is in the last slide. B times the length of a circle. And do the right side. Every one of these steps y'all are capable of, and you'll get a result at the end. That should look very familiar. Yeah, call us over a few stones. I want you all to derive this because it's cool. Derive something in 3 lines that took us like 2 entire PowerPoint slides to do before. Ta-da! So what expression? Does that equation look familiar to you? B equals mu naught I over pi r. For an infinite wire, but it took us 3 lines instead of trig sub integration awfulness.
Did you say we determined positive or negative based off
Yeah, I should have put the magnitude of the field. Yeah. So this should be better. Magnitude of it would have been better. All right, so again, we just go through the motions. The left side just turns into b times 2 pi r because b is a constant. dl is the length of a circle. Done. Equals mu naught. How much current do I have inside this red dotted or this blue dotted thing? I. Well, that was easy. Great. Rearrange this for b. Mu naught I over 2 pi r. Ta-da! We derived the expression for an infinite wire in 2 lines. 3 lines if you include the original equation. It's great. This is why Ampere's law and Gauss's law are super nice. They let us solve problems that would otherwise take a lot longer. So just rederiving the equation for an infinite wire. Now you can only use Ampere's law for it has to be an infinite wire. That is something important. It does not work for a finite wire. So symmetry and all that jazz. Okay. Now, to get into this idea, I mentioned this prior. The direction of current matters. So in this picture, I have 3 wires. The one on the left is 3 amps going down. The one in the middle is 2 amps going up. The one on the right is 4 amps going down. And I have a Ampere loop, just a random loop that was drawn here. And that loop is enclosing the 2 wires on the right. Find the I enclosed. Now, I didn't define which way is positive and which way is negative, so let's just pretend like it's magnitude of current enclosed. So is the current enclosed 1 amp, 2 amps, 6 amps, 7 amps, or 9 amps? Give you all a whole minute on this. You can do this math in your head. If you're never going to find it, I mean, you can evaluate. Look at the change. All right, 10, 15 more seconds. We don't want to spend too much time with this. Go with your guys. Check other people around you. The net magnitude is and I even tell you the direction of current matters. It's in the problem. All right, 5, 4, 3, 2, 1. So we are going to define direction matters. So if they're in opposite directions, they're going to cancel each other out. So what's enclosed? I got a 4 amp going one way, and I got a 2 amp going the other way. So we're going to subtract it. So my current enclosed is 2. Direction matters. Direction matters. Now you may be like, what possible scenario would have current going in different directions? That seems so weird. It's literally every single wire you all have ever interacted with. Current was going in 2 directions. Every single wire. Literally, this cable that's plugged into my computer, current's going one way and then it's going the other way. Why? You need a closed loop. How many prongs are there on a plug? 2. Why are there 2? And at least 2. There's sometimes 3. Sometimes you have 3 wires. Current goes into your device, current goes out of your device. It has to, otherwise it's not a closed loop, and the current won't actually flow. Every single wire you all have ever used is a 2-way street, at least. At least. It might have more than 2. Another example, this is a coaxial cable. So like a physical example, this is something called a coaxial cable. You all have seen these before. They're often used for cable internet, but they're used for a lot of other things. A coaxial cable, why is it called coaxial? Just break up the word. Co means multiple, axial means axis. It's 2 wires centered around an axis. So this is a coaxial cable. Oh, look, I got a middle wire, and then there's an outer metal wire. Current goes in one direction and goes out the other direction. So this is an example of a what it might look like. It's just an easier one to see. You got two pathways, in and out. So every single wire did this. And we care about that. So presumably if these currents are the same and you did Ampere's law, you'd actually find the magnetic field outside of this is 0. Which is kind of important. Sometimes you want your wires making magnetic fields. A lot of times when it comes to this, you don't want them because it'll actually interfere with other things in your system. Anyway, it matters. Direction matters. That was the whole point here. Now, this problem. I'm going to let you all draw the picture of this, and I really hope that you look at this picture and like, this looks slightly familiar. I have a very thin wire that takes up no space. It carries a current of 3I, and it's at the center of a thicker wire with radius R, which carries a current of I. What is a magnetic field at some point R, little r, that's less than big R? I want y'all to draw a picture of this first. Draw a picture, and then figure out what you're solving for in the problem. And I'm really hoping when y'all draw this picture, you're like, that looks kind of familiar. Oh, and to clarify, to draw this picture, you could draw it, we tend to draw like cross sections of the wires whenever we draw them. So you don't need to draw a three-dimensional picture. For example, like when we did this one, we drew a cross section of the wire, as if the wire was like coming out of the board. It's just easier to draw. So draw like a 2D slice of this wire. Yeah, and we use a similar technique. So we have two wires. So you do the ratio for one of the wires. So you're going to find the current closed for each one. Yeah, so if I look at the thin wire, how much of the thin wire is inside the option? So we'll have all of that current plus the current of the thick one. Yeah, and it's the same technique that we use for Gauss's law for the other one. Yeah. Yeah, we're finding the field somewhere in between, inside the wire somewhere. Yeah, pick some random spot, make a dot there, and then draw like a little R to it. Yeah, if you were outside the wire, it would be a very simple problem. It'd be much simpler.
Are you treating the thin wire as like
infinitely thin?
So like R would not be inside the thin
No,
wire? Okay.
no. The thin wire has no.
Yeah.
Otherwise, it takes
Ideal
up space in the other one, and
Yeah.
that makes life hard.
So the thin wire has so R's outside the thin wire, while inside the thin wire. So little R is outside the thin wire, while inside the thin wire. So that's what you're finding. So the entire big ring has a current of I, right? So you're finding what rate, like, you know what I mean? What percentage of the big ring's I do you need to use? That makes sense. That's what I enclosed. So use the I enclosed law to find what percentage of the total current is. So the total current is the total current and total area of the enclosure. So the enclosed current and enclosed area. Same thing. It's uniform. So you're using the area enclosed to find what basic percentage, this is proportionality, what proportionality is the I enclosed.
Yeah.
Because you're using the angle
Like, yeah, total. Like this is gonna be.
All right, so just drawing the picture. I got a big circle wire, and then I got some thin wire inside it. I didn't specify this, but let's assume the currents go in the same direction. I should have specified that. I didn't assume they go in the same direction. Both currents are in same direction. All right, great. So this is my little wire in here. That's going to be 3I. This is going to be my radius R, capital R. Now, it just says some point little r less than big R. So literally anywhere inside the object will work. We draw our dotted loop. Actually, before I even do that, hopefully you all are looking at this and this looks kind of familiar. This is just like the problem on the test. Now, it is obviously different because that was Gauss's law and this is Ampere's law. That one said find the electric field due to a sphere with a tiny little sphere in the middle. But we're going to use a similar, it's very similar way of thinking. It's just 2D instead of 3D. So we're going to do this. And then you all just need to do Ampere's law, which sounds, that's just do Ampere's law, right? Do the steps I told you all. Great, there's this. Just follow the steps. The left side is really easy. The left side is always basically the same thing. Really, the challenge comes to can you find I enclosed? And the key to that, I have 2 wires here. Find the current enclosed by each wire and just add them together. That's the key to solving this problem. So, try if you haven't already. Yeah, follow those steps. The left side should be easy. You just look at the PowerPoint slide, you'll see why it's so easy. It's always the same thing. The right side is really the only one.
Yeah, but what if little r just equals big R?
Yes, that is a very important. Yeah.
Okay, what if it almost? What if it's 0.999? Essentially would be. You're gonna have to go around you 3I.
Yeah. You can assume a uniform current density, a constant current density. You have to.
Ooh, that.
Oh, I bet.
Artificial reality. I'm sure it's
No. It's really interesting.
I think they're using it as a product.
I'm really curious. what they have, like what level, if they actually have you all building models, or if they have you just utilizing existing models.
It's probably them. It's probably a both have almost. It's like how did they train it? Like how did they train it with image generation?
I wonder if it's even that level. Maybe, yeah. No, I think that's good. I genuinely believe this is like the new internet in terms of the impact of it. Which sounds like a big claim, but there's so much money going into this that a lot of people feel the same way.
When you take into account when you plug in, you're like, you just add it.
Yep, you just add 3i plus that.
So basically, you can multiply and divide by both.
Yes. All right, so just to give you all the next step, phi times 2 pi r equals mu naught. How many wires do I have here? 2. So let's label them. Let's label them wire 1 and wire 2. Wire 1 and wire 2. So we need to find the I enclosed for wire 1 plus the I enclosed for wire 2. Why? Because they each have some current. Question. All right, let's do the easy one. Wire 1. That's my tiny little wire. How much of that wire am I enclosing? All of it, none of it, or some of it? All of it. Great. So what's the value of it? Easy. The next one. All of it, none of it, or some of it? Some of it. Now we got to do that whole. What are we going to do? It's outlined here. If you have some of it, find the current density. That's the thing I mentioned to you all before. This is a 2D slice. A 2D slice. So we're not going to use a volume density. We're going to use a area density. So this one, my density is uniform. Meaning if I take my total current and I divide it by my total area, that's going to give me the current density. That is also true if I take my enclosed current and I divide it by my enclosed area. The example I give for this is a piece of paper. I'm going to steal a piece of paper. All right, great. This piece of paper has some density to it. How can I find its density? I could take its mass and I could basically divide it by its area. It's basically two-dimensional. How can I do it for a tiny little piece? The same exact thing. I could take its mass divided by the area of this piece of paper. How do the two densities compare? They're the same because it's a uniform density throughout this object. That's the idea. You never actually need to calculate the density. You just use that ratio. Your paper's moving now, sorry. And then just rearrange this for I enclosed. So I enclosed equals, rearrange it. Do some algebra. What is the area? You can see what shape it is. I'm not going to tell you what shape it is and let you think about it. It's what you want it to be. And find it, and I'll give you all the final answer. The answer will be up here on the right when you're ready for it. But make sure you can get there. Don't just look at the answer and think how to get there. Get there and then look at the answer. And then we put that there so you can check your work.
I don't know if
So it ends up being a ratio of areas. You're basically just finding out how much of my area do I have. How do I find out how much area I have? I take the area enclosed and I divide it by the area total. Where did I get that from? Algebra. I just took the equation on the left and solved for I enclosed. What is my area enclosed? It's the area enclosed by that blue dotted circle. What's my area total? It's the area of the entire thick wire. It's a circle. What's the area of a wire? Or a circle shape? Pi r squared. So I enclosed here is going to just equal I. That is the current in my big fat wire. That is the total current. What is the area enclosed? Pi times little r squared. What's my total area? Pi times big R squared. What happens to the pi's? They cancel. Then you just plug that in. So we get B times 2 pi R equals mu naught times 3I plus I times little r squared over big R squared. Divide the 2 pi R to the other side. Factor out the I. And you get the answer that I get in the top right. B equals mu naught I over 2 pi R times 3 plus little r squared over big R squared. And this is about as simplified as you can make this. You can do other things to it, but in my opinion, it doesn't make it any simpler looking. And this looks very similar to the test problem where it was like one of them plus the other one, the ratio. Now in that case, there's a ratio of volumes instead of a ratio of areas because it's Gauss's law versus Ampere's law. But yeah, you need to know how to do this process. You need to know how to get those currents enclosed and add them together. Just like on the test, you all needed to figure out how to get the charges enclosed and add them together. So, cool. All right, so that's that problem. All right, now the last thing in this PowerPoint is teaching you about solenoids. So we're going to build a solenoid. You're like, what's a solenoid? I'm also going to teach you what that is. First step. I got 2 wires, one pointed out of the page, one pointed into the page. My question is, what is the direction of the magnetic field at some point equidistant between them? That point P. Is the magnetic field at point P to the left? Is it right? Is it up or is it out of the page? We get lots and lots and lots of practice with these right-hand rules.
That's the one where you either curl your fingers or you use like a line. So the one at the bottom is showing in the page, right? So your thumb is up into the page. You can either curl your fingers or you can do like on your hand and then you palm it in the right, yeah.
And I recommend either draw this on your paper or have it on the screen in front of you. If you try to match up your hands to the whiteboard, that can be fine, but it's much easier when it's right on the paper in front of you, so you can make sure your fingers line up right. That just it ends up being helpful when it's on the thing physically in front of you, really close to you, so you can make sure your fingers line up right. You don't have to do that, but it's a strategy. It's what I would do. I draw things. You need to be able to draw the arrows. Circle around it, that circle. What about this one? Go to the right.
Oh, yeah. I did it wrong.
All right. 10 more seconds. I think we're looking pretty good on this. Yeah, we're looking good. All right. 5, 4, 3, 2, 1. Right-hand rule is very much either you know how to do it or you don't. It's fairly dichotomous, unfortunately. Either you can... my experience has been either people get it consistently right or they have no clue how to do it. It's looking pretty good here. But yeah, we point our thumb in the direction of current. The top one's out of the page, so it makes a circle. Just to remind you all, this is making a magnetic field that's a circle around it. That's the whole, what the right hand does. And that circle is going counterclockwise. So at the bottom, the top one makes a magnetic field to the right. On the bottom wire, also makes a circle. That current is going into the page, so that circle instead is going clockwise. But at point P, both magnetic fields point to the right, so the answer is to the right. So that's with the whole circle method. All right, now something I kind of tricked you all. I didn't trick you, but fun fact: this is what a loop of wire looks like from the side. You're like, what do you mean this is what a loop of wire? If I had a loop of wire that was coming out of the page at the top and into the page on the bottom, this is what a 2D slice of it looks like. This is a loop from the side, a slice of a loop. The loop is coming out of the page on the top, and then it kind of circles out of the board, and then it comes into the board on the bottom. And if we know that, you all can do a little trick. You can do right-hand rule 2.5. So if this is a current-carrying loop, like a loop that's doing this out of the page and into the page, you can just do right-hand rule 2.5 and get the exact same answer. So that's actually what I wanted to model here. This is a loop of wire, and the magnetic field inside of a loop of wire, in this case, will point to the right. Now, why do I mention that? What if I had a bunch of loops? An infinite amount of loops. Which way would the field point inside it? If one loop pointed to the right, what if I have an infinite number of them? Will the field point some other direction or the same direction? Take your guess. Go with your intuition. I say it's not equally distanced from both rows. Doesn't matter. The answer to this will be true everywhere inside this. So I got an infinite amount of loops just kind of stacked next to each other. All right, give y'all 20 more seconds. I don't want you to think too hard on this. All right, in 5, 4, 3, 2, 1. All right. Look, if one of them makes it to the right, a whole bunch of them make it also to the right. That's kind of the quick answer here. Now, to show you all why, we're going to use the same. If we looked at like call this one, wire 2, the magnetic field due to wire 1 is directly below it. That's directly to the right. Wire 2, that's also, now it's a little bit weaker, but because it's a little bit farther, but whatever. Still points to the right. What if I pick some wire 3 that's up here? Well, that one's going to point up to the right. Why? Because of a circle and all that jazz. If I then pick this wire here, wire 4, which way is that going to point? Down to the right. Oh my gosh, there's symmetry. One points up to the right, one points down to the right. What happens to the up-downs? They cancel. So long story short, it's to the right. Now, explaining why it doesn't matter on distance, where I was located, that gets a little bit more funky to explain. I'm not really going to bother too much with it for the sake of time. I just don't think it's too worth it. We're going to see it with Ampere's law. We're going to prove it mathematically. But just know it doesn't actually matter where I am in this wire. And I'm just going to prove it to you mathematically if you understand conceptually. I'll explain another time. All right. So what is a solenoid? It's a bunch of loops of wire. Now, it doesn't mean a loop stack. It's not just like a bunch of hula hoops stacked on top of each other. It's a coil. A coil will look like a bunch of loops stacked on top of each other. You all can see this is a cross section of that coil. It looks like the picture I just showed you. Now, something very important about this wire is the outside is covered with an insulator. It sounds like, why does that matter? Current takes the path of least resistance. Why should it go in a circle if it doesn't have to? If this is just a conducting wire with no insulator, the current would just go straight up the wire and ignore the circles, because why would it care? Why would it go in a circle if it didn't have to? It is very important that when you build a solenoid, that the outside has an insulator around it. That could be rubber. It could be a paint. Like there's this very thin kind of painted material. You probably wouldn't even be able to tell. It depends on your application. But the current needs to go in a circle. That's very, 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 very important. And to do that, we coat it with an insulator. Okay. We are now going to solve for the equation field, the equation for the magnetic field inside this. Now, one of the questions that comes up is why? Why am I solving for the equation for the magnetic field due to a slinky? What's the value here? It's because these are present in almost every single electrical device out there. So if you're like, what do you mean? I haven't seen these before. Well, circuit board. Let me see if I can spot one on a random circuit board. Most of them have it. Sometimes they're a little hidden. Oh, what's that? I don't want that. Just want to look at the picture. Does that one have it? Kind of, sort of. Let me see if I can spot one. They're on a lot of circuit boards. Sometimes they look a little different. It's easier. I might have to force the matter. This one's going to be... Anyway, I'm just going to look up one. We call these inductors. So if you all have ever seen a circuit board with these like wires and loops, this is a solenoid. And you're like, but this one looks like a donut. They just wrapped it to save space. Wrapped it on itself. So these are really, really common. Sometimes they are covered. Sometimes you can actually see the copper wires wound together. But yeah, you can imagine taking a slinky and just bending it back on itself, and it's the same thing. These are super, super, super common elements inside circuitry. We're going to learn why next week, what they're used for. Okay, so let's find the magnetic field. And we're going to do, it's going to be a little silly how we're going to do this maybe. I just remember when I learned this first time, part of it feels a little silly, but it's fine. Like I'm not doing anything wrong here. Just one step of it, you're going to be like, that feels a little silly, but it works, so it's not silly. All right, we're going to do Ampere's law. I'm just going to straight up tell you it's going to be a square. Now we're going to understand why. Remember, we're doing Ampere's law. We're doing B dot dl equals mu naught I enclosed. We're going to look at the left side of this equation. Why did we choose a square? Remember, our goal is to either make that integral a constant or to make it zero. That's our goal. So we got 4 pieces of the wire here. We're going to look at each piece in turn. So we're going to do the integral of b dot dl. We're going to do each piece. So piece 1. Now remember that this b dot dl is the same thing as b times dl times cosine theta. We really care about that angle. That's going to show up later. All right, on wire 1. Here's my wire 1. Which way does the magnetic field point? Not a trick question. Just check out the picture. Left. Which way does my path going? Left. Look, there's a little arrow here. That's DL. Which way does B point? The same direction. So what's the angle between them? That's convenient. Cosine of 0 is 1. And it's everywhere the same on that path. Also, the magnetic field is the same everywhere on this path. Why is it the same everywhere in that path? Because this is an infinitely long solenoid. If I moved it left, right, you wouldn't be able to tell. So, this integral, B dl cosine theta. B is a constant, so it comes out. Cosine theta, that's going to be 0. Cosine of 0 is 1. So we just get B times the integral of dl. What's the integral of dl? L. Yay, that's nice. Let's look at the other sides. Here on the left side, which way does my path point? I just drew it in red. Up. Thank you, thank you. Inside the solenoid, the B is to the left. Outside it, it's to the right. What's the angle between something to the left and something going up? What's cosine of 90? Great. So B dl times cosine of theta. If the angle is 90, this just equals 0. Boom, left side's gone. If that's true of the left side, it's also true of the right side. For the exact same reason, the right side is also going to be 0. You do not need to know this derivation. I'm just showing you it so you don't think it came out of thin air. All right, here's the silly part. That third side, it is not drawn to scale. Where is that third side located? Let me draw it to scale for you all. Now, I made this a rectangle. Where is this third side actually located? Keep going. That's as far as I can zoom out. It's infinitely far away. The third side is infinitely far away. Why? Because I'm allowed. Nothing stops me. I can make that square whatever shape I want. Why did I make the third side infinitely far away? What do you think the magnetic field is going to be infinitely far away from this thing? Great, the integral is 0. So this is the part that feels a little silly, but this is actually a really common technique in physics, is anytime we do like a path, we can like take part of the path and just put it infinitely far away to make that side 0. Nothing stopping me. No police to say you're not allowed. So anyhow, the third side, this is going to seem stupid, but it's I'm not breaking any rules. B is 0 infinitely far away. So it's just 0. Boom. So what does my B dot dl equal? B times L. The left side, B dot dl, if you add up 0 plus 0 plus 0 plus BL, it equals BL. Cool. We did the left side. Let's do the right side. The right side is going to be this mu naught I enclosed. How do I find I enclosed? I know this is not clear here, but this is a bunch of loops of wire. Each of these is a wire. Every one of these X's is a wire. If each of these wires carries a current I, let's count how many I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So what's my current? What's my current enclosed? 14 times I. I got 14 I's. So my total current, my current enclosed is just 14 times I. Now, back to what this actually represents. Remember, this is a solenoid. Every time I have the current going around, that's a loop. Every time this circles around, it's one loop, one loop, one loop, one loop. So what is my current enclosed? It's N times I. N is the number of loops of my solenoid. How many loops is that? N. However many it might be. So put all the pieces together. B times L equals mu naught N times I. Just solve for B, and that's the equation for a solenoid. Mu naught N times I over L. It's how many turns per length. How tight are my turns? How many turns can I fit in a certain space? And that'll show up in the next slide a little prettier. But that's the derivation for it. You do not need to know the derivation. This formula will be given on the formula sheet as well. Mu naught I times N over L, where L is the length of the solenoid, N is how many loops I have in the entire solenoid. Something we can do to make our life a little easier is we can use a lowercase n, and that's turns per length. So that's just how many turns per length, capital N over L. And that's the third equation for magnetic field. We have magnetic field due to an arc of wire, we have magnetic field due to a straight wire, and now we have magnetic field due to a solenoid. And the solenoid is actually the one used in circuitry. They're called inductors, is what their terminology when they're in a circuit. Solenoid and inductor is the same thing. It's just a solenoid in a circuit. All right, something very important here. Do you all see R anywhere in this equation? No. Do we care about the radius of the solenoid? No. The magnetic field everywhere in the solenoid is the same. This might sound familiar to another piece that's in a circuit, a capacitor. What's special about a capacitor? The electric field is the same everywhere inside a capacitor. Solenoid, the magnetic field is the same everywhere in the solenoid. Magnetic field in solenoid is the same everywhere. Changing the radius changes nothing. Now, we're assuming an infinite solenoid here. In the real world, we don't use infinite solenoids, so, But in this ideal situation. So this is why we have to learn about solenoids. The same reason we had to learn about infinite planes. A capacitor is two infinite planes. A solenoid is an infinite number of loops next to each other. And the more turns you can put, the bigger this can be. These often have hundreds or thousands of loops. A lot of these. The ones I showed you in the picture didn't actually have a ton of them, but if you really want to make a strong magnetic field, you need a lot of loops. More loops, more field. More field, maybe that's better for you. More is not always better. Sometimes you do want a weaker one. It all depends. All right. So, math. This is just trying the equation. This is pretty straightforward. What's the magnetic field inside a solenoid with 200 turns per meter and a current of 3 amps? Try it out. I'll even put the equations for you on here. How kind of me. Notice I didn't tell you the radius of the solenoid. Notice I didn't tell you how long the solenoid is. You just needed 2 pieces of information to solve this. Notice I didn't tell you where I'm asking for the field. I just said inside it, somewhere. Doesn't matter where.
Does the number of turns per lane need to be always meters?
Yes. Yeah. Always base units. If you have it per centimeter, you do need to change it. Yeah. For example, in this case, this would be 2 turns per centimeter. And 2 and 200 are different numbers, so if you plug them, you'll get different answers.
Yeah. Is it the mu that's making it? What's making it have to be meters?
So all of our equations are tuned to specific base units, and we always
And they just use meters when they measure.
meters is base unit. Yeah, so meters is the base unit. So every equation, if it has a distance anywhere in it, you better be in meters. If you had mass inside of it, you better be in kilograms. If you're in current, you better be in amps. Yeah, and the easy proof there is if this instead said 2 turns per centimeter, which is the exact same thing, if you plug 2 in, you're going to get a different answer than 200. Yeah. Oh, and mu naught is 4 pi times 10 to the minus 7, in case you always. You can change the value of mu by putting a metal rod inside of it, but we're not going to bother with that. Oh, yeah. Yeah, I don't know. So often my understanding of circuitry is most cases where you could use an inductor, you could use a capacitor. This is So I don't actually know the benefit of an inductor versus
Very small, yeah.
I think it. I guess one use case is that it helps resist current spikes, so it helps protect your circuitry. An inductor is used to smooth current fluctuation. Because I know you can. Depending on your arrangement of the circuit, it has certain reasons you can grow. It's just whether you're taking the direction you want the current to flow or like it's going. Alright, give you all like 30 more seconds. Doesn't matter if it's plugging in the numbers for the equation. This equation currently is not on the formula sheet, but I will add it to the formula sheet. It should be on there. I just have to add it.
Yeah, it's really weird.
Is we here supposed to be
Because it's technically a unit from an field, but it's not. It's not the one that uses equations right now. I don't actually know.
Isn't Gauss's because they were smaller than
One Tesla is 10,000.
Okay, smaller. Yeah.
So one Gauss is smaller than one Tesla.
So I think that's the one that's like most
Are very weak. Yeah.
Standardized.
All right, 5, 4, 3, 2, 1. Boop. I mean, this is just plug in the numbers. 200 is lowercase n. This is I. You get this. You get 7.54 e to the minus 4 Tesla. Why Tesla? Because that's the base unit. Gauss is a unit for magnetic field. It is not the one that the equations spit out. If you wanted to put this in Gauss, the answer, so 7.54 e to the minus 4 Tesla is the same as 7.54 Gauss. They're just off by an order of times 10 to the minus 4. So I was just asking the TAs if they had a sense of who uses Gauss, and I don't know who does. So, but it exists. It's a thing. All right. We're not going to solve this one, but I'll leave it for you for funsies. Great. All I then want to point out here is a brushless motor has a bunch of solenoids in it. So you all can check out this link. It's kind of a cool thing. So this is it's not animated on here, but if you go to the link, it's animated. It's a really cool website that goes through how motors work, and it's got some nice diagrams. So you can see here the current is constantly kind of flipping, and by flipping the direction of current, it makes a different direction of magnetic field. So when the current, I can't pause this, so it's just going to keep, it's really hard to. When the current goes one way, it makes a magnetic field, let's just say into it. When it makes a current the other way, it makes a magnetic field out of it. And by flip-flopping that magnetic field, these solenoids basically act like permanent magnets. And so when the field is one way, it's attracted to the north end. And then when it turns the other way, it's repelled by the north end. And so you get this constant pull, push, pull, push, pull, push by flipping the direction of the current. Your magnets are set. But by flipping the directions of the current, this red end is attracted to the blue end. This blue end is attracted to the red end. When the red end is here, it's getting repelled by that end. And it's just constantly flipping it. This is maybe a more complex one. It's a little slower, but you can see the idea. It makes the current go in a certain direction to make this happen. The permanent magnets in the middle, set. You don't change those. What you do change is an electromagnet is a solenoid. Every single electromagnet out there is a solenoid. It's a solenoid is a magnet that you can change the value of and the direction of it at will. And that's very, very, very useful for, electric motors is like one of the big ones. You can also use this to lock doors. Every single, an electronic lock, a lot of them are just a solenoid that turns on. And when the solenoid turns on, there's a piece of metal and it just holds it really strong. Some of them. You do run into the problem that you don't want a door to be unlocked when the power gets turned off. That's obviously not ideal. So whatever. Feel free to check this out. It's pretty cool. There are also some motors where instead of using permanent magnets, it just uses all solenoids. Just solenoids everywhere. And the benefit of this is you might get a little bit more control over things. So here, it doesn't quite show it, but in the middle here, they have a solenoid that they can change the direction of the field on, and it spins, and yay. And then it gets, pictures and things, and check it out. For engineers, this should be stuff like mechanical, aerospace, electrical. If you want to make stuff move, this is what you're going to be doing. A motor of some sort, and you should probably understand how that motor works. And everything I've taught you is pretty good. You just would have to understand the transistors and the logic there, maybe.
Do generators just work the opposite?
Yeah, that's a great question. How do generators work? Yes, they are the opposite, and that is the nice segue into the next thing I'm going to teach you all. So I've now taught you how to go from current to motion. What we're now going to jump into is going from motion into current, the opposite. So I've shown you how to take electricity and make things move. Now we're going to figure out how to make things move to make electricity. Rule of thumb with physics, every equation in physics is kind of reversible. Like, if you can go one way, you can generally go the other. Time, you can make go backwards. It's one of the big question marks. Every single physics equation I've taught you all works just as well if you make time negative. So that's one of those big question mark things for us. What does that mean? I don't know. You can think about it yourself. Anywho, Faraday's law, i.e. how generators work. What a great segue. Didn't even plant that. So Faraday's law, it's called electromagnetic induction. This is going to explain every single way we produce electricity except for solar power. Coal power plants, nuclear power plants, wind turbines, generators that you could buy at home, the alternator in your car, hydroelectric dams, thermal power. Every single one is using the exact same thing, specifically a turbine. You spin a turbine and it makes electricity. How? We're going to learn how. But every single one makes something spin. And by spinning that thing, it makes electricity. And I'm going to teach you how it does. And what's really cool, in like 1 week, I can give you enough to understand it. So to do this, though, we need to understand everything we've been talking about. Magnetic fields. We're going to need to understand flux. Flux is something that came up on test 1. It's coming back up again. Area vectors. Force into magnetic fields, voltage. So yeah, we're going to first talk about what flux is. We're then going to talk about something called EMF, which is called the electromagnetic force. Sounds really fancy. Sounds really complicated. Pretend like the word EMF is voltage. It's going to be voltage. There's a reason we use a different term for it, but it doesn't really matter. We're going to figure out how to find that voltage, that EMF. We're going to figure out the direction the current's made. And then the last little bit, we'll talk about changing electric field, changing magnetic field for like one slide, not too much. All right, why do we care? Generators. Every single way we produce electricity, except for solar panels. Solar panels are the one thing that this will not teach you how it works. So then the question is, how do solar panels work? Semiconductors, more complicated. Now, flux. You all have done flux before. So let's see if you remember. If I have an electric field pointed upwards with a magnitude of 8 newtons per coulomb, what is the electric flux through that plane? If the plane has a length of 2 meters and 3 meters, the plane is flat on the xy plane, and its area vector points in the z direction, which we'll say is like up. Find the flux. If you're like, what's flux? Look through the formula sheet. Ask someone around you. Yeah, the big question is, do you know the equation for it? If not, find it, because we're going to use it. If you're not sure and you can't find it in the notes, Google it. It's just an equation. If it's just recall, check GPT. really good at just facts. Okay.
Well, okay, I mean, your question.
I've never felt more burnt out. Same. Oh my God. At least I'm
Probably gonna be studying for 20 hours. Good news is one of the lowest grades dropped, but I got a B is the lowest drop. I'm probably gonna have to be in a class. Yeah, I feel so exhausted. It'd be so nice. Last exam, it was like, I studied a lot, so I have like 88. I used the entire grade for 4 questions.
All right.
So
Give you all about 10 more seconds. I think we're looking pretty good, though. All right. 5, 4, 3, 2, 1. All right. So it's always good to draw a picture. So I got a plane. There's my plane. It is useful for you all to be able to draw in 3 dimensions. As much of a like artistic task as that may feel, it is a useful skill to have. If you want to draw a sphere in 3 dimensions, you just draw a sphere. Like you do this enough times, you figure out ways to like make decent looking things. I'm not an artist and I can do this, so you can do it too. This side's 2 meters. This side's 3 meters. I have a field that points up. And I'll leave it like this for now. The equation for flux, now it's an integral technically. But we always did flux where E was a constant and A was a constant. So we're just, spare ourselves a little bit. I never had you all do flux where it's not a constant, and I will say you're going to be spared that as well. Remember, the dot product between vectors is the same as the magnitudes times cosine theta, where theta is the angle between the things that were dot product, E and A. So the question is, which way does A point? Y'all tell me, which way does A point? Anyone got any ideas? Does it point up, down, left, right, into the page, out of the page? Great, it's up. How do we figure out the area vector? You take your pencil and you put its eraser on the thing and it points in the direction. It's a vector that's perpendicular. Great, so what's the angle between these? In this specific problem, it's 0. So 8 times 6 equals 48. And then the units just come from the things you multiplied. Yay! It's flux! What is flux? It's how much of the field lines go through. Oh, and I put B here. There's no B in this problem. What is flux? It's how many field lines go through it. When the thing's flat, you can see all of them are going through that. Wow, so much flux. As I rotate it, I can get less and less and less. All right, great. Do it with magnetic field. I didn't even give you the equation. It's the same one. Just replace E with B. Find the magnetic flux. It's the same numbers, but now my plane's at a 30-degree angle. So be careful. See if you can draw the picture. That's probably more useful than the math, honestly. If you can't draw a decent picture of it, you're going to have a hard time. I don't know. If you can draw a decent picture of it, it will make your life easier. And then after this problem, we'll take a break. We'll do a little bit more, not too much.
Is it above or below the plane?
Yeah, 30 degrees to the plane, to the XY plane. So the plane itself is 30 degrees above the XY plane. Yeah. So when I say the plane is at a 30-degree angle, that means it's like tilted up 30 degrees. The flat plane is like, it's like a inclined plane is at a 30-degree angle. Not the area vector is at a 30 degree. It's always a pain. There's a reason we use area vectors.
Oh. So it's 932, which is yeah, it's got 48 sides.
Yeah, it's
Oh, what a nice picture. It was great. It's a great skill being able to draw 3 dimensions. Yeah, I actually got this answer wrong in the lecture class I taught this morning. I did in the last 2 minutes, said the wrong answer. I went up and I realized I was wrong. I kind of wanted it to be 60, so that's my first class. Oh, silly.
Wait.
This one's for like 90 points.
Yeah. Sure. So let's take flat. It's flat. Let's go to the area vector point. So if I then tilt this thing 30 degrees, how much did my area vector tilt?
wait, hold on.
I mean,
That was
Because if this tilts to 30, the area vector tilts to 30. If it used to be this, it's now 30 degrees. That's kind of the 20. Oh, you did. Alright, I'll give y'all like 10 more seconds. I think most of us have answered at this point. We're going to solve this in 2 ways. You want to?
It's the opposite.
Alright, in 5, 4, 3, 2, 2, 2,
1.
2, 1. Great.
Alrighty. Okay. So we need to first look at what is our area vector going to be. Well, that's just normal to the plane here. So it makes, this is our area vector. It's normal to the plane. And if the plane is tilted 30 degrees and the electric field is going up, like this, then, sorry, magnetic field, you're right.
magnetic field. Then their angle of separation is also going to be 30. So we just do the same thing as before. It's going to be the magnitude of the magnetic field times the area times the angle of separation, which here is 30 degrees. Here we have 8 times the same area, which is 6 times like root 3 over 2. Altogether, it's about 41.57 Tesla meters squared.
Yeah, and to figure out that this angle is 30, there's a couple tricks to this. In the last problem, which way was my area vector pointing? It was pointed up. If my plane is tilted 30 degrees, how much does my area vector get tilted? 30 degrees as well. So that's like the, I don't know what you want to call that, logical way. If you want to do geometry, the way you can do geometry is that this angle here is 90 degrees, as ugly as that is. So this and this are 90. This is 30. No, that's not 90. This is 90. That makes this 60. And then this is 90. So that makes that 30. Great. That's the geometry way. I tend to try to do this logical. Like if it was flat, what would it be? And then how much did it actually get tilted? And which way did things move around? That's easier for me than doing the geometry. All right. We'll go ahead and take a breather. Look, there's the equation. Wow. It's an integral, but if it's a constant, it'd just be a cosine theta. So anyway, there that is. Take a breather. I'm going to run away for a second. We'll resume in like 5 minutes. We're still going to finish early today. We're not going to go all the way till time. But we will cover a bit more things. The more we get through, the better buffer time we have to get.
She said that, yeah, like before it was like my skills, work experience in leadership projects. She was like, make it your experience project skills. And that's why I saved both copies and I'm angry on it. I'm like, I know this is that I think she stated because like one of the problems with the paper sorry is like a because I told her I was like I'm super I have notes because if I use one thing I can that was not like so I think that's why she was like put your project everything else is minute or so.
What? Nope. Are you in? How's not that hard? Is that how you really feel? Oh, so you're that's the undergrad student.
Yeah.
Exactly. Yeah.
I honestly have favorite kids. I think he's good at the moment.
Our feels hot. You just fluid.
Oh, mean, I like the weird cheese. I think it's. I also just think it's interesting. Like they made the tires, they made themselves dedicated. That's been a week. It's hilarious.
Space or newly.
Here, can I use your?
But maybe someone else, Richard, he raised a good point that was like, but they're probably important to know, considering the human body is full of them. That's a good point. So,
That's all. This is
I
for
didn't
you.
do her much.
Literally, only good. Yeah. Black keys are pretty good. The doors.
I learned a little bit.
People are strange and going on the ceiling. Or sorry, people are strange and painting.
Oh, I did absolutely nothing by what I did to prepare for that was
Let me see a gold on the ceiling. That's the black key. It's gold on the ceiling. It's pretty simple stuff. I mixed them with the metal.
yeah. Sure, accidental why? We don't want to.
He's pretty easy. He's just fine.
This is as far as I made it for lecture class.
Is he like a Japanese
With the exception of getting the answer right.
You know what's fun.
All right, so we'll go ahead and get started again. Look, magnetic flux, I'm not going to lie, not very exciting. Not very exciting. You're like, why do I need to know magnetic flux? The parts that's cool, understand Faraday's law. If you don't know what flux is, it's one of the equations in the law. So we have to understand flux to actually do it. It's like, yeah. So flux is something like, why do I need to understand this flux? The reason flux exists is so we can do Faraday's law. If we don't understand flux, you can't do Faraday's law. You'll see what I mean when we see Faraday's law. It's like half the equation. So, flux. You need to know what flux is. Oh, look, there's Faraday's law. What is Faraday's law? The EMF induced equals the change in flux over time. Faraday's law says the change in flux over time equals the EMF. You're like, what the heck is EMF? I want to point out something. What does it say the units are of EMF? EMF is just voltage. Pretend like EMF is voltage. Every time you all see EMF moving forward, pretend like it says the word voltage. The reason it's not voltage, the reason we call it something different is because I might have to look at an example. Like I might have to show you all an example to describe why. Whenever we talk about voltage, we always talk about a difference in voltage, but you can't actually measure a difference in voltage with it. It's like it's just one weird. It acts like voltage, even though it's not voltage. That's kind of why. As for all purposes, mathematically, it acts like voltage. Conceptually, it also kind of acts like it, but there is some funky things. All right, at the bottom, this is a fun fact, just a science thing. Faraday discovered it. It's called Faraday's law. Joseph Henry discovered it a little bit later. So this is, I put the phrase Henry got scooped. This is a phrase in the research community. If someone gets scooped, what basically happens is two people are independently working on something. And if someone discovers it before you, then you've got scooped, which sucks, which means that they get all the credit and you get like very little. It's who discovers it first that gets the award, the recognition. So it's just one of those fun little science things. It happens. You don't know what everyone's doing research on, and sometimes you can spend years working on something, and then all of a sudden another research group publishes some results, and you're like, wait, crap, I was doing that. And then you can kind of say, I guess they're right. And you get maybe some small recognition, but you're often neglected. Another example of this is like Isaac Newton did. And some of this is also cultural. Isaac Newton discovered calculus, but someone else discovered it independently in India. I don't know what their name is. So what is that? You know, there's some of like that. And some of that's culture as well. And it gets a little tricky. But anywho, Fun facts. Faraday's law, it would have been called Henry's law if he was just a little bit quicker. That's all right. He got inductors named after the unit for inductance is named after him, so it's fine. Okay. Now, just to make sure that we're cool with this idea of treating EMF like voltage, if I have an EMF in some circuit with a resistance R, what will be the current generated? Hint, pretend like instead of that symbol, this symbol for EMF is epsilon. This is the Greek letter epsilon. Always good to teach y'all some Greek. It's a squiggly, it's a backwards 3. That's small. How do you draw it? You draw a 3 that's backwards. That's small. It's kind of fun to draw. But yeah, you all can do this. You know how, if it was voltage, you would know how to do this. So pretend like it's voltage. Will the current be epsilon over R, epsilon times R, R divided by epsilon, or epsilon squared R? Pretend like epsilon is V. And then you got this. The current understanding is you got a loop of wire and it's experiencing this. You couldn't just put a voltmeter in 2 parts. So normally we say along the wire the voltage is the same everywhere. Yeah. But that's not true here. You have a loop of wire experiencing change flux. And so it's like, do you just put it one at each end? No, it doesn't work that way. It's across the entire loop. Yeah. So it gets really. You can't just like put multimeter probes and actually.
I guess unless you have infinite meters.
At least if it's like a closed, circle loopy thing. So that's why it gets really weird.
Yeah.
Oh wait. Yes, you're correct.
Trying to find as many nonsensical ways to combine these. All right, what say you all? Why? Great. Alright, what y'all get? Great. That's all one. What y'all get? What? Great. I'm just trying to prove to you all that even like it has zero.
The base equation is
Great. Fantastic. All right. Cool. All right. 5 more seconds. It's looking good. 5, 4, 3, 2, 1. All right. So, Y, V equals IR. So, I equals V over R. So, just pretend like V is EMF. And there you go. That's the idea. Now, this is going to be a quick, and if this doesn't make any sense, that's okay. Why don't we just call it voltage then? Why don't we just call it voltage? And the reason is so we're going to have a loop of wire. This is just foreshadowing of what's to come. And we're going to learn that when the flux changes, it makes a current. So, it makes some current in some way. Great, there's some current. If I wanted to take a multimeter and measure this EMF, this voltage. Remember, we always think of voltage as a difference between 2 points. There's a high and a low. Where am I going to put my multimeter leads? Like, if I put one lead here and one lead here, I'm actually going to only measure half the EMF. I'm only going to measure half the actual voltage that's happening. If I take one lead and I put it here and I put the other one right next to it, I'm going to measure no EMF. So this is where this is why we don't just call it voltage. It's not because there's actually a point of high voltage and a point of low voltage. It's not actually happening, but it's as if there was. So that's the really weird idea here. This EMF, the current will flow as if there was a change in voltage, but there actually isn't a high and a low voltage anywhere in this circuit. There's nowhere in this loop where it's a high voltage and nowhere on this loop where it's a low voltage. But the current's flowing as if there was. So that's the weird idea here. This is why we call it a different name. This is why we don't just call it potential difference, because there's not actually a potential difference anywhere in this circuit, but it's acting as if there was. So, all right. So, this is a quick summary. If there's a change in magnetic flux, there's an EMF. If there's an EMF, there's a current. We made electricity. Yay. That's it. That is what Faraday's law says. Now all we have to do is, how do we make a changing flux? That's the next question. Because if we make a changing flux, we made current. If we made current, we made electricity. We made charges move. You made the flow of electricity. So how do we change the flux? That is the next logical question. Great. You tell me. Think about it. I'm going to go around and ask you all, what are the 3 variables that we can change in magnetic flux? They're the only 3 variables in the equation, but one of them might not be apparent. One of them you might have to write out things, ask some people around you. 2 are going to be obvious, the 3rd one maybe not as much.
Dude, no way.
You've already done it. We had a problem where we changed the theta.
No, I know.
Yeah. Oh yeah, but how do we change the theta? So think of the first 2 problems we did in class today.
No, I didn't.
What's the difference between those 2 planes? So if I keep tilting that plane, what am I doing to that plane?
And it's important that it's over time, right?
I'm changing the angle. Let me take your all's paper. I'm changing the angle. What do y'all call this motion? Or how would you describe it? It's rotating. Great, that's every single turbine out there. Just spinning a coil. Alright, what y'all come up with? What are the 3 things? The first 2 are pretty straightforward. How do we change the angle? Boom, that's every turbine out there. All right. So what do y'all think? What are the 3 variables? Y'all tell me. Area. Great. That's 1. What's another one? Magnetic field. What's the last one? The angle. Now, changing the magnetic field, changing the area, that's not going to be too tricky to explain how to do that. The area is actually the weirdest, whatever. How do I change the angle? What would I physically do to an object to change the angle? Rotate it. That's that's a turbine. Every single turbine is just spinning something. What am I spinning? I'm either spinning magnets or I'm spinning the coil itself. Either way, stuff is spinning. I'm changing the angle. Yay! All right, so here's a nice little summary of this. You can either change the angle, at which point, the field changes with time. You can change the angle. Everything else is a constant, or you can change the area. You could technically change more than one of these at a time, but we're not going to do that in this class. You would then just have to do chain rule and yada yada. We're just going to change one thing at a time for the sake of simplicity. All right. Now, again, the area and the magnetic field ones, those ones are, the rotation one is the most interesting. That's how we actually do it in the real world. All right. Great, let's try it. A circular loop of wire has its radius shrink from R2 to R1 over t seconds. The area vector stays parallel with the magnetic field. What is my induced EMF, my pretend voltage? We're never actually doing this. No one's making wires shrink or expand. That's really functionally quite difficult to do, but mathematically it works. Yeah, so the 0 volt, pretend like all these had volts after them. And I specified average here, so you didn't have to do a derivative. All right. What do y'all think? Explain your rationale. So what's changing in my flux? Is it my field that's changing, my area that's changing, or my area? Okay, cool. What's the equation for area?
I think you might explain the process.
Oh, that's the derivative. The change in area with respect to time. Now, when we're looking, yeah, so it's a part. So here it's d that over dt. Yeah, but if we're doing average, we can just do delta. Yeah, so it's the change of flux with respect to time, so it's a derivative. But if we do average, we can just look at the endpoints. Make it delta instead. And here the magnetic field is staying constant, the angle is staying constant, so those come out. The only thing that's changing is the area. So, yeah, that d is not a very, d is not like a distance, that's like dx dt, dv dt. It's the derivative. So d is not a variable, d is differential with respect to something. So like dx dt means the rate of change of position over time. So it's d flux dt. Let me write. This d is not distant. Just like, yeah, and if it's an average, just like if you so when they're changing to make it more yeah, it's exactly. And yeah, this flux can be applied to any. Alright, 5 seconds. I think we're pretty good on this though. Yeah, okay. 3, 2, 2, 2. That's alright. Everyone got it right anyway, so I'm just gonna leave it open. Alright. EMF equals technically I guess there's a negative, but we just don't really care about the negative. We're gonna look at the negative later. The negative has conceptual meaning. Mathematically, it doesn't really do anything for us, but it does have a conceptual meaning. So for now, we're just gonna say d flux dt. Now, if it's average, an average means that my derivative turns into just delta. In algebra-based courses, we always just use delta because they don't know derivatives, which is fine. But yeah, anytime you see average, we just care about the endpoints. So what's changing in this? Everyone got it right, so be confident. The area, great. So if I write this, it's delta B times A times cosine theta over delta T. B is a constant. Cosine theta is a constant. So we just care about the change in area, delta area over delta time. And look, everyone got it right, so I'm not going to spend any more on that. Yay. Great job. Fantastic. So that's, again, no one's actually doing this. No one's taking wires and making them bigger or smaller because, like, functionally, how would you even do that? But it is mathematically possible. Now, what if you have multiple loops? What if I have one loop and then another loop and another loop? If one loop has a surface area A, then two loops will have a surface area 2A. And three loops will have a surface area 3A. So this is just an update to the equation. If you have a bunch of loops, just multiply it by A. If one loop makes a certain change in flux, then 10 loops makes 10 times that change in flux. 100 loops, 100 times a change in flux. Yeah, so if y'all want to make a bunch of voltage, you need a bunch of loops of wire. The coils inside of these turbines, again, we're talking thousands of loops of wire here. Because the change in flux tends to be pretty small, but look, if I just make 1,000 loops, I have 1,000 times the voltage. Great, I've generated 1,000 times the electricity, quote unquote. I'm using hand-wavy terms here. So this is an updated version of the slide. It's got an N in it now. Same thing, but with a capital N. And yeah, this is the only equation you all really need to understand in order, like this is the equation that explains all turbines. Which is kind of, I don't know, I think that's cool. It's such a small equation. And it's the foundation of all electrical generation except for solar. This is all you need to know. Like this law in and of itself. Now, obviously, when you engineer things, there's other things you got to think about. You got to make sure these wires don't get too hot. So you start to care about the thickness of the wires and things like that. The real world's more complicated. But this fundamentally is all we need. All right. Great. Yeah, I just want to get... So we're going to do this, and we're going to do rotation, and then we'll kind of call that, I think, pretty good. 50-turn coil has a diameter of 15 centimeters. The coil is placed in a spatially uniform magnetic field of 0.5 Tesla so that the face of the coil and the magnetic field are perpendicular. So this means that the area vector and the magnetic field are parallel. Find the magnitude of the EMF induced in the coil if the magnetic field is reduced to 0 uniformly in 0.1 seconds. So you just write the equation, what's changing, find the change. We're finding the... Yeah, if it's uniformly, that means it's linear, which means, again, we don't have to do a derivative. Don't worry, we'll get to do derivatives. I know you really want to. We will. But we're keeping it simple now. We're just going to use deltas. And I'll put the answer up here. Yeah, we won't spend too long on this because it is really simple. If you mess up this problem, it's probably because you didn't convert your units right. Oh, I stole it. All right, the answer should be 4.42 volts. Now, making a magnetic field of 0.5 Tesla is hard. That's a really strong field. Yeah, so we'll just get through the next few slides on rotational stuff. And then I'll set us up. Next class, we'll figure out the direction the current goes.
Yeah, hopefully. We'll see. I'll check it tomorrow. I don't want to worry about something.
Yeah. But
I remember everything that we saw.
again, we're kind of ignoring the negative here. We only care about the magnitude. All right, so there it is. Area is a constant. The angle is a constant. The field is the only thing changing. And then you just got to be careful that you converted centimeters to meters. You got to be careful it says diameter and not radius. You're like, why did you do that? Why did you put diameter instead of radius? When you all are measuring things in the real world, you're going to be measuring it diameter. With calipers and things like that, you're not going to generally measure radius. You're going to take your calipers, put them at both ends, it's going to give you the diameter. Most equations we use radius. You got to get, you're like, that seems mean. That's how the real world works. So, you know, you gotta be careful with diameter versus radius. So yeah, we get 50 times pi r squared, which is going to be pi times 0.075 squared times 0.5 over the time. If it goes to 0, my change is just the 0.5. And you get the answer. Now, this voltage is actually pretty good. Getting 4 volts out of a thing is that's a lot. It's really hard to actually make a lot of voltage. That's why I told you all 0.5 Tesla is an incredibly strong magnetic field. The lab this week, I'm actually going to do something, I think it's cool. We'll see what you all think. The lab this week, we're going to measure the Earth's magnetic field using our phones. So there's an app we're going to download called BiFox, which basically your phone has so many sensors in it that you don't even realize. One of them is a magnetic field sensor. You're like, why does my phone have a magnetic field sensor in it? See if y'all can take a guess real quick. It's not. It's related to GPS, the compass. Your phone determines north by just measuring the Earth's magnetic field. It doesn't actually. You don't need to be connected to the internet to figure out which way north is. Your phone has built-in magnetic field sensors to determine which way north is. So we'll utilize that. It's a really cool app. Your phone has accelerometers in it, which measure acceleration. They have gyroscopes in it, which measure rotation. They have light sensors. You're like, they have light sensors. It's a camera. You may be like, that sounds stupid. No, like it can detect the intensity of light. It has sound sensors in it to detect. And you're like, sounds? It's a microphone. But these are really accurate sensors that your phone has so many of them. And there's a cool app that lets you actually generate graphs of the data over time, which is cool. So we'll show that on Thursday. Anywho, great. What would be the induced EMF if it were rotating? So, let's see. What did I have here as far as getting this? All right, we're going to figure it out together. All right. It's not too bad, but I do need to give you all a refresher on rotation, and I call it a refresher. It depends whether you did learn rotation in Physics 1. So I need to give you all a quick refresher on angular velocity and frequency. They are not the same thing. Angular velocity is omega. It's a little w. It's not quite a w, but it looks like one. Angular velocity is defined as the rate of change of angle. It is radians per second because, again, degrees are a real thing. Sorry, radians are a real thing. Degrees are made up. So the units for this are radians per second, or sometimes it's just listed as hertz, which is kind of inconvenient because radians isn't technically a unit, which is kind of annoying for notation purposes, but it is what it is. But this is the definition of angular velocity, rate of change of theta. It's like regular velocity, but instead of distance, it's angle. Instead of measuring distance per second, it's angle per second. It's an angular velocity, the velocity of your angles. All right, the other thing I need to remind you of is another word. So this might be called angular velocity or angular frequency. Which one is right? Both. Those are both the same term for they mean the same thing. Angular velocity, angular frequency, same thing. They're both W. Regular old frequency. If you see the word frequency in a problem, it is not the W. It is F. What is F? It is the rotations per second. So if I say something's rotating at 300 times a second, that is F. If you want it, and generally we need to go from F to omega. That's a pretty common thing. Now, something that shows up is F equals 2 pi over omega. Why am I doing all of this? Why am I mentioning all of this? Because turbines spin at a certain rate, an angular velocity. Or you could describe it with a frequency. Both are fine. You just need to know which one you're working with. Notice neither of these showed up in our equation. Let me just remind you all there. The flux equation was dBA cosine theta dt. And you're like, none of these show up. But hopefully you can kind of see where they might show up. Anywho, express cosine theta in terms of F. See if y'all can do it. So we've been writing cosine theta, but we're going to start writing it in terms of the frequency now. And if you can do it in terms of frequency, you can do it in terms of omega. So is cosine theta in terms of F, cosine ft, cosine 2 pi over F, cosine 2 pi t over F, or cosine 2 pi ft? And you might need that last slide to help out with this. We're going to assume a constant rate of rotation. We're going to assume a constant rate of rotation. That's true of pretty much every turbine out there. A constant angular velocity, a constant frequency. Not integration, no integration yet. So we're just trying to express theta in terms of that. So good. Okay. Yeah. Sorry, that's it. We can basically just say our change in theta is theta. Our change in time is time. Okay. If we just start at 0. Yeah. That's the kind of an easier way with that helmet. But yes. Yep, that works. Yep. That'll do. Yeah. What do y'all think?
Well, think about it.
What do y'all think? What equation?
Wait, actually, I'm pretty sure what it is.
No, it's that's F is wrong.
No, but I think this would be.
Yeah. No, the left one's correct. F is rotation per second.
Oh, yeah. It's 1 over F.
But it should be T.
Yeah.
Your last slide. Isn't it omega over 2?
There's a chance. Yeah. All right, there is a typo here. Good catch.
Oh, it's
Yeah, whoever caught it, great catch. I always mix up the order, but yeah. All right, we're looking pretty decent here. I'll give you all 10 more seconds or so. We are assuming a constant frequency. We're assuming a constant angular velocity. We're not going to have any of that speed up or slow down. That makes it too complicated. All right. In 5, 4, 3, 2, 1. All right. We're going to use the equations that I just showed you on the last slide. Specifically, if we have a constant, we're going to use this omega equals delta theta over delta t. Why is that useful? So let's just rewrite that as theta final minus theta initial over time final minus time initial. Why am I doing this? Let's just make my initial 0. Why not? Great, equals theta over time. I'm allowed, I can make my starting angle 0. We tend to make our starting time 0. This is just to kind of show you all that omega t equals theta. This is, if you're like, whoa, this is weird looking. Hopefully y'all are cool with this, x equals vt. It's the same thing, but instead of x, it's angle. Instead of angular velocity, it's regular velocity. It's the same thing as like kinematics, so great. So how is that useful? We can take that. So cosine theta equals cosine of omega t. But I didn't want it in terms of omega. Omega equals 2 pi f. So great. Cosine equals 2 pi f t. This is this is the way we write something rotating. When something is rotating, this is called, anytime you have something that varies, that's kind of rotating, oscillating, doing some periodic motion, we will either write cosine of omega t or cosine of 2 pi ft. This is a very normal thing to do for things that rotate, that do a periodic motion, doing the same thing again and again and again and again and again. This solution, so physicists, we do something called the harmonic oscillator, which is just something that wiggles back and forth forever and ever and ever. It turns out you can model any periodic motion. What is periodic motion? Something that repeats itself. A planet orbiting a sun. A wheel making a spin. I don't know. More things. Spring. Anything that does the same motion again and again and again and again and again. All right. Circular coil with loops in an area A. Rotate the frequency F about a diameter, as I don't know what it says, diameter is axis. About its axis. It's like a coin spinning. Something that's spinning about its axis. The loop is placed such that there's a constant magnetic field perpendicular to the axis of rotation. What's the flux at time t? And what's the EMF generated in the coil, assuming B and A are aligned at t equals 0? So 2 questions here. So draw this picture, because it's like this axis stuff might sound a little weird. It means I got a loop that's spinning in a field that points such that the flux actually is changing. So find the flux, find the EMF. You're going to have to do a tiny bit of calculus. But it's really easy calculus. You learned it in Calc 1. One step at a time. Find the flux, then find the change in flux. This is not one that you can do with deltas. You need to do some actual calculus. And this we'll kind of end with this one. This will be our last problem for today. That's good enough.
We don't have a quiz saying if you do
Because quizzes are typically on Mondays. Right? Are they on Mondays?
Usually. I think we had our first one Wednesday, but we also, that was kind of just a weird deal. I have my thermo test at 7:30, so we have a quiz.
You won't let me do that.
I think we're sure. Plus you in the house. Well, he announced it like in person.
No, not in person. He didn't announce it in person. He sent an email at 5 o'clock that day.
You're right.
He did announce it in person, but the second first.
Point being that he still had a way of verifying us whether about the you're mocking the way that I see it. Wait, I said no.
Yeah, quiz number 4 is
Let's go.
Yeah, and then you differentiate it.
Wait, what? So what are we doing between now and that quiz, bro?
then our test is in almost exactly.
So no quiz next week?
Is there a form? Just a form.
It's Q1. I'm pretty sure it is. Exactly, that's what I'm saying.
Yeah, and then they were like, you should totally like manage like with your.
Wait, what?
All right, what's the equation for flux, y'all? That's literally part A, is just write the equation for flux. What is the equation for magnetic flux? BA cosine theta. Yay! That's the answer to part A. Part B. What are we solving for in part B? The EMF. What is the equation for EMF? Oh, and there's an N in here as well. Yeah, we can't forget that. All right. N times a change in flux and change in time. So just take the flux, put it in there. Two things are a constant. One thing is changing. We talked about there's three variables that can change. B, A, and theta. Now, notice in this problem, actually, so I told you that was the answer to A. That is not in terms of the variables given in the problem. What is that? So this is not actually the answer to A. We need to do something to this. What do we need to do to it? What you all just did last problem, the clicker question. This problem says frequency. Write theta in terms of frequency. What is theta in terms of frequency? It's the problem we just did. Cosine, this is why I had you all do that. It's to prepare us for this problem. Great. And this can hopefully show, hopefully it is very abundantly clear which of these is changing with time. Plug it in, take a derivative. B is a constant. A is a constant. What's left over is not. Take a derivative. It's a nice simple Calc 1 problem. You're not sure what to do, just start plugging the things in. Always. Yep, everything's very bad. Plug any numbers in. Any numbers you could plug in. You check players.
That's you.
It's I think it was lost. So this positive is
You want to repeat that?
So it's
Alright, shall I take a derivative? Just try it. Yeah, it's really easy. It's a calc 1 integral or derivative. Try this, y'all, if you haven't done it. Just take this and put it here. B is a constant, A is a constant. Take a derivative with respect to time of everything else. It is quite simple, but actually do it. Do the derivative. Yes, that is. It's like yeah, it's differentiating with respect to that variable.
Because you could like throw that out. Yeah.
Yeah, you're differentiating that expression with respect to D. B is a constant, A is a constant, so pull them on out.
I don't remember where the best picker is, but he kind of showed that as part of this, he kind of showed that you can decompose it into a function that shows that one wave is traveling this way, and the other half is traveling yeah. So yeah. Yeah. It's like one has speed C, one speed C. It's pretty much it. It's like a trig identity to get there or something. Actually do it. I don't know if she wants us because from the examples we have, we just used this formula, plugged in whatever initial values and boundary conditions, and then just left it at that. It feels like too little compared to all the other problems. So I'm like, am I not? I should just stop there. Figure that out.
All right, there's the answer. What's the derivative of cosine? Sine. Negative. So it cancels out the negative. Not that we really care about the negative. You got to do chain rule. Whatever's inside also needs to come out. The 2 pi f needs to come out. Now, this answer is the exact same thing as this answer. NBA times omega times sine of omega t. Remember, 2 pi f equals omega. That's just the definition of omega. All right. So, great. This is the equation that gives us the voltage generated by any kind of turbine, honestly. Assuming B is a constant and roughly is. All right. So that's going to be, I will just show you, what are we going to look at next class? We're going to look at this equation and say what happens as omega increases. What changes? Just foreshadowing. But we'll do it next time. And great. You all know how turbines work. You all know how generators work now. Basically. You know enough.